1, 2, 1, 2. Okay, everyone, just a quick check that you can hear me in the chat, and then we'll make a start shortly. We'll get 9 people in already. That's great. We'll just start as soon as we get a few more bodies in the door. But just a little check, because I've got software now. I've got OBS software, and if you could just put a little yes, or we can hear you in the chat, then I know to make a start. Okay, we get a few people saying they can hear, which is great. So we shall just wait a few more seconds. I'll clip this, and then I'll put this online later on, and I'll clip it to actually start. So we'll just have a few more minutes just when people get ready. If I could recommend that you have perhaps some paper and pen, and you try and work along with me. This is going to be a chemistry session based on paper 1, which is C1, C2, C3, C4 and C5, and it's the AQA version, so it's kind of specific to AQA, and this exam we'll be doing tomorrow morning. Okay, let me get a few pages ready here. I'm checking the software is all up and running, so we shall begin pretty soon. Okay. Alright, so I think we'll make a start. Just to sort of fill you in a little bit, last week I did the chemistry one, and there's a few technical hiccups in terms of when I tried to switch the screen to show my browser, the microphone disconnected. So what I actually did, I downloaded OBS Studio, if anyone knows. It's pretty neat, it's pretty smart for doing streaming, so if it goes wrong tonight then I've not practiced it enough, but I can switch between various things. So I've got this title screen, I've got the visualizer, which is there, and I've got a webcam, which is there. Hello. I won't use the webcam as much as I probably will, and I've got my browser on there as well, so I can show you some things, maybe some online PowerPoints. So that's the idea. Let's make a start with the visualizer. Now, this is chemistry paper 1, so this is really about the fundamental things that the fundamental things that you have to know that might help you tomorrow. Okay, so I can't cover everything, so I'm doing this at 7 o'clock tonight with the hope that you've done some revision, and this is going to help top up or maybe consolidate what you've done. And also it's the if you have you're going to do some more revision tonight, this might give you a sort of a good launch pad to do some more revision, maybe give you some hints. So that's the idea behind it. So let's begin. I've got this on the screen just now. This is a diagram of beryllium, and this is a nice place to start, not because it's beryllium, but because it's what we consider to be the modern view of an atom. Now, I should have picked my colours a little bit better, but we've got 4 blue dots in the middle and 5 green dots in the middle, and we've got these 4 red dots around the outside. Now, hopefully, given that you have chemistry tomorrow morning, this is the model of an atom, but because it's beryllium, which dots are which? Okay, that's the question. Now, we need to be able to look at information. So before we analyze this and get the numbers and get the facts and everything, you will have to contend with this tomorrow. This is a periodic table. This is a one, I made this. I didn't make up the table, but this is my design. I made it up about 12 years ago, and it's stuck ever since. And only recently I found a typo. You will have to use this tomorrow. However, there's a few changes, a few catches to it. Okay, this whole section down here will not be given tomorrow. You're going to get AQA's version, which is this. I don't know why. We just have to accept that this is the one they give you. So the lanthanides and the actinides aren't given. Those tend to be the cool ones, like uranium, neptunium, americium, so on and so on. So this is what you have to deal with tomorrow. Let's refresh our minds what we have to do in terms of numbers. So beryllium is over here. In beryllium, the symbol is Be, and it is a number 9 at the top and a number 4 at the bottom. So let's figure out what those numbers actually mean. So we've got beryllium, we've got Be, and then we've got 9, and we've got 4. So again, you have to know these basic facts. Okay, so this number down here that's called the atomic number. If this is something you know, guys, great. You have to know it and you have to be confident doing it. And this up here is called the relative atomic mass. Now, why am I doing this? It makes it a bit easy. Why? So there's a catch, because I've not told you which is which. I've not told you the green ones, the blue ones, the red ones, but we have to know a few facts about atoms. And it is that they are electrically neutral, which means they have the same number of protons and electrons. So if we know that the red dots are representing electrons, we have 2 in the first shell, and then we put the other 2 in the next shell up. Then we know that the electrons are -1 charge, and their mass is negligible. Okay, it's about 1/2000th the size of the other 2. Okay, so we know that's electrons, but here's the catch. If they're electrically neutral and I've got 4 electrons, then which of these is protons? Now there's 4 blue dots and 5 green dots. It's an atom, they've got to be electrically neutral, so I've got to have 4 of the ones that are plus, and that means that our protons are the blue dots, because I've got 4 of them. Charge is +1, and we say that their mass, we'll call it 1, sort of relative to other ones. Now by default, if that's protons, electrons, these must be neutrons. And I've got 5. And we see these have no charge, and their mass is 1. So protons and neutrons are similar in mass. There's a slight difference, but it's tiny. And then electrons are much smaller, 1/2000th the mass of neutrons and protons. So I knew that the blue ones were protons because there's 4 of them, and I have to have the same number of protons as I do electrons. And so the atomic number tells us the number of protons and also the number of electrons. The relative atomic mass, so the top number, tells me the number of bits in the middle in the nucleus. So there's going to be the 4 protons and the 5 neutrons. Okay, that's the basic model for an atom. You have to know it. You've also got to know about isotopes. So isotopes, I'm going to keep it really simple. They have the same protons and they have different neutrons. Same number of protons, different number of neutrons. You can obviously write it out better tomorrow morning. Same protons, different neutrons. How might that look in terms of the periodic table or maybe symbols? Well, we could take a look at carbon. Carbon has 6 protons and 6 neutrons, therefore it is 12 in the mass number. 6 protons and 6 neutrons. Okay, that's carbon. An isotope is going to be same number of protons, so 6. But quite a cool isotope, which is radioactive, is C14. Which means both of these have 6 protons. This one has 6 neutrons. This one has 8 neutrons. So same number of protons, which makes it carbon. Different number of neutrons, which makes it an isotope. So that's a little summary of isotopes. And I should point out on the table, so I'm going back to this, the top numbers are rounded. So, you know, we get carbon 12, that's the main one. In the real periodic table, these numbers go off to quite a few decimal places. And the one you'll get tomorrow, the sneaky little one, which is chlorine. Now, chlorine has a relative atomic mass of 35.5, which means it's got, so let's have a little glance at chlorine for a second. We know that say for every 4 chlorine atoms you have, there's going to be one of them will be so 17 protons and 37 is the mass number, so it's going to have 20 neutrons. 3 of them are going to be Cl17 and 35. Now there's a way to do, there's a little bit of maths which I want you to revise on your own, but essentially of all the chlorine atoms that you can find in nature and molecules and packaged up in various things, for every 4 that you find on average, 3 will be 35, 1 will be 37. And so that averages out to be 35.5. Okay, so that's given in the periodic table. You have to revise a little bit of maths that calculates that number. I kind of do it in terms of averages, but there's a little bit of percentage work that you have to do. So that's a little summary of atoms. Okay, so what else do we have to know about the table? We've got to know group numbers. Okay, so we've got this one here, and we have the group numbers 1, 2, 3, 4, 5, 6, 7, and 0. This used to be called 8, but then we changed it to 0. And what do these numbers mean? Okay, well, we have to look at electrons. Now the bottom number tells us the number of protons, the top number tells us the number of protons plus neutrons, but the bottom number also tells us the number of electrons. And so if we look at this little thing here, I'm sure your teachers in various formats have given you some of these before. These are showing the first 20 atoms and then the electron shells or energy levels surrounding those. So I'm going to use my red pen again, since I did that previously. And hydrogen has atomic number 1, so it's got 1 proton and 1 electron, and obviously this was done already, that goes there. Helium I'm not going to do all 20, don't worry, that's not the purpose of this. Helium has 2 protons, it must also have 2 electrons, and that also goes in this first shell. But hopefully you know by now that the maximum capacity for this first shell is 2. Beyond that, we have to add electrons to subsequent energy levels. So lithium, which is atomic number 3, we put 2 in the first one, and then we get, that's 2 done, we need to put 1 more, which is going to go in the next shell up, which is there. If we do the same for sodium, so I'll put this down here actually, let's get 3, let's get 1. This sodium has atomic number 11. Okay, and yes, for those that are asking, I am Scottish, and there is a joke, there's a comedy sketch where there's 2 Scottish gentlemen in a lift, and they have to use the voice command, and they say 11. Yes, I've seen it, and I chuckled. So sodium has 11 protons. It must also have 11 electrons, and we fill in the shells until they fill up. So we put 2 in the first shell, that's fill up. 8 is the capacity of the next one. 1, 2, 3, 4, 5, 6, 7, 8. That must fill up. I've used 10 electrons so far. I've got 1 left over, which goes there. And hopefully this is just a recap. You know that if the atom is in the first column, the first group, it's defined by 1 electron in the outermost shell. Potassium has 19 electrons. It goes 2, 8, 8, and 1. We go to group 2. Then these are defined by having 2 electrons in the outer shell. Beryllium, the one I just did, has 2, then 2. Magnesium has 2, then 8, then 2. Calcium has 2, 8, 8, 2. And so the group numbers in the periodic table are describing the number of electrons in the outermost shell. But we get to group 0, then there's a bit of a change, because it used to be called group 8. These are the noble gases. And so what's happening here is sodium has 10, and that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the outer shell is full. Helium's outer shell is also full. It's got 1 shell and it's full. The question, Oscar, no, you don't have to learn them off by heart. I'm just showing you that's a really good question actually. Your job tomorrow is not to memorize these numbers, but to know what they mean. Okay, so I've gone through the page. So I would look at this and say, right, oxygen is there. Oxygen has 8 and 16. I know that means 8 protons and 8 neutrons. Sorry, 8 protons and 8 electrons. And because it's 16 at the top, it's got 8 protons plus 8 neutrons. I should be able to look at iron. And iron has 26 protons and also 26 electrons. And it's got 30 neutrons because the mass number is the 26 protons plus 30 neutrons. So you don't have to memorize them, but you have to know what they mean and how to use them. And the atomic number and the electron structure gives us this definition of group numbers. So if we go back to this group 0, argon is 288. Okay, so the outer shell of argon is full. And so the way I like to describe it is, it's called group 0 because there's 0 space. 0 space left in the shells. Okay, we're full up. The outer shell is always full up and full. Group 7 is called halogens, and these are defined by having 7 electrons in the outermost shell. So fluorine has 9. It's going to be 1, 2, that's full up. Then we have 1, 2, 3, 4, 5, 6, 7. Chlorine, we just mentioned, it has 17 protons, 17 electrons. That has 2, then 8, and then 7. 1, 2, 3, 4, 5, 6, 7. So group 7 means they have 7 outer electrons. I'm sure you know that, but it's just a little recap where the group numbers come from. Some properties that you have to know about for these. So these are called the halogens. These are called the noble gases. And group 1 is called alkali metals. The name comes from the fact that when they react with water, they produce an alkali solution afterwards. Now, these are very reactive. These are reactive, but there's a difference. As you go down group 1, so we'll ignore hydrogen for the moment. As you go down group 1, I want you to notice that the outermost electron is always moving to one shell further out. So if we continue this on to rubidium and then cesium, we're going from, so lithium has the outermost electron in the second shell, sodium is on the third shell, potassium's on the fourth shell, rubidium is on the fifth shell, and cesium will be on the sixth shell. Now that outer electron, which it loses to form an ion, we'll discuss that shortly, in reactions it loses that electron, it's moving further away from the nucleus. And so we say that the electron is less attracted to the nucleus the further down the group you go. And that has a few implications in terms of melting point and boiling point, and also reactivity. I want you to recap or revise what happens with group 1 reactions in terms of melting point and boiling point. For group 7, because it's easier for them to gain an electron than to lose 7, again in reactions, then particularly ionic ones, then we add electrons to here, and the space, so we can add electron to fluorine, the space that we can put one in is close to the nucleus. As we go down the group, the space, or the available position to put an electron is in the outermost shell. That shell, because the atoms are getting bigger, that available space moves further away from the nucleus, so there's less attraction between this incoming electron and the nucleus. So as we go down the group 7, it gets less reactive. So down group 1, they get more reactive because they can lose its electron much easier. Down group 7 becomes less reactive because it can gain an electron, but it becomes harder to gain it as you go down, so less reactive. So that's a little summary of those two. Now let's have a think about the periodic table in a bit more detail. There's a few things you have to know, so I'm going to refer to my textbook for a minute. The first one is the development of the table. Okay, so a little bit down here, I know it's quite hard to read, but you have to know about John Newlands. And John Newlands proposed the law of octaves, and he noticed that every 8 people started to discover elements. The first one to be discovered was phosphorus, believe it or not. Then we started to isolate, and we started to discover more, and people started to group these by different properties, okay, atomic weights, and also perhaps some reaction properties. And what Newlands noticed was every 8 it seemed to repeat the properties, so he called them the law of octaves. That's John Newlands. But there's a problem, because after the first 20 or so, we had to place copper in with lithium, sodium, potassium, and copper is not as reactive as the alkali metals. So the problem was there. Along comes the Russian chemist called Dmitry Mendeleev, and he proposed that we group the elements in order of atomic weight. So you go from left to right, they get bigger. But he also had this repeating pattern where similar chemical properties went in columns or groups. So the rows are called periods and the columns are called groups. And what you have to know for tomorrow is that he left some gaps. Okay, that's a key principle. He left gaps. And he predicted things like, I think he called it AQA aluminium, and he was able to guess or predict the density and the melting point and the properties of this element that hadn't been discovered yet. He named it AQA aluminium, and it turns out that when I think it was gallium was discovered, it matched pretty much like for like the properties of what Mendeleev proposed. But he was also, so you have to know he left gaps, which were later filled with his predictions when they discovered the elements. But another cool one is he was brave enough to swap them around. The classic example is these two. I know you can't see it too well, but this is tellurium, and this is J, even though it should be I for iodine. Even though it's going left to right, the numbers are getting bigger. He swapped these two around because iodine exhibited similar properties to other group 7. Tellurium exhibited similar properties to this group 6. So even though the weights are the wrong way around, he was brave enough to say, actually, sometimes it isn't always on the weight, it's also on properties. So that's the two things you have to know about Mendeleev. He left gaps, and he was able to swap the order around, and he could predict the properties of elements that would later go into those gaps. Okay, so that's a little bit on Mendeleev, not too much, but again, that's up for you to revise. Okay, so let's move on a little bit. We've got a lot still to cover, and let's look at bonds. Okay, chemical bonds, and the key behind any chemical bond is electrons. Okay, so let me just go, I'll leave it on there just now. The key to it is electrons, and you need to know that there are 3 types of bonds. There are covalent, ionic, and metallic. Okay, so here's a little quick summary of those 3. Let me just do these in different colours. So we've got a non-metal there, And let's just get the colours ready. So we have a non-metal, and we have a metal, and then we could have a non-metal and a non-metal, and then we could have two metals. Again, I'm sure people know this, but I'm just repeating this just so we know what our definitions are. A non-metal and a metal, we could put this as a little minus, as a little plus. That's going to be our ionic. And the key to this is, Freddie, good question. Is there a reason why first to be discovered? I don't think so. I think it was 1511 it was discovered. People obviously knew silver and gold and some other elements, but the first to be identified as an element on its own standing was phosphorus. Yeah, good question. Again, not what you have to know for tomorrow, but again, it's interesting to know these things over and above what we have to do to pass the exam. Ionic is this one here, and this is a transfer. Now, I like to call it a swap, okay, but it's not really. It's transfer of electrons. This is covalent, and this is going to be a sharing of electrons, and this is metallic, and this is going to be a sea of electrons. Okay, so swap or transfer, share, and a sea of electrons. And we may not focus too much on metallic. I want to just cover these two because you will be asked tomorrow to answer a question on ionic bonds and also one on covalent bonds. So let me just switch from my visualizer. I want to go to my, not the webcam, but my browser, and I want to just show you these really quickly, just to get us thinking about it. And I'm just going to check that this is working. Hang on, let me just click on this. That should come up as a little slideshow. Okay, so hopefully, let me check in my software. It's still, you can still hear me now, even though I'm switched to the slideshow. This was a problem last week where I switched to slideshow and I was disappearing. So we've got here we have two. Let me just check. Okay, it's working. So I've got my iPad in front of me, which is on the delay. So I'm seeing it a little bit behind. So I've got the slideshow up there. Great. So here we have carbon and we have hydrogen, and we know that carbon has 6 electrons. So it's 2 and then 4. We know that hydrogen has 1 electron. So we put that one there. Now we use what's called dots and crosses to distinguish which electrons come from which atom. So we're looking at covalent bonds first of all. Now we tend just to drop the inner shells, so we get rid of those. So we're only looking at the outermost shells because those are the ones that do the work or the swapping or the transferring in bonds. And because we've got hydrogen needs 1 electron to be full or to be seen as full, because it's got 1 shell, it needs an electron to be full. Carbon needs 4. Okay, it's got 4, it needs another 4 to be full. And so we swap, or we don't swap, we share the dot electron from hydrogen with one of the crosses from carbon, and we draw it as an overlap. And we put those electrons in the overlap area, and because it is 1 pair of electrons, we call that a single covalent bond. Now, the hydrogen's happy, it's seen an electron, it's got its own electron, it's getting 1 shared with from carbon, it's happy, that hydrogen, but the carbon isn't. Carbon needs to have another one come in, do the same thing over here. Again, that's going to be another single covalent bond. Then we get another 2 to go, so 1 comes in, and a 4th one comes in, and now we have CH4. This is methane. And so, we've got 4 single covalent bonds, and we draw that as overlap areas. Now we can actually get rid of so we can draw this in another way. We can get rid of the circles and the dots and just have lines. So a single covalent bond can be represented, this is called the structural formula, as a single line. We can do another one with carbon and oxygen. So carbon has the 6 electrons, oxygen has the 8, and the arrangement is 2 in the first shell for oxygen, then 6 in the next shell. Carbon's 2 and 4. Again, we only considered outermost electrons, so we get 4 on carbon, we get 6 in the oxygen. So oxygen needs 8 to be full, to be stable, so it can get 2 of those from carbon. So we have an overlap area where there's 2 from the carbon and 2 from the oxygen. Now right now oxygen can see 8, so it's happy. Okay, I know it's not the word to use, proper chemist. I just thought of the chat there. The question from Daniel: do you get a formula sheet for the exam? No. Any formula you'll get, you have to know, and I'll show you those formula later on today. You will get a periodic table. Okay. Yes, face revealed. Yeah, I've been in the sun this weekend, so a little bit red. Guys, back to this. So we've got, because oxygen needs 2 to be stable, or it needs 2, then we get 2 from the carbon, and because it is 2 pairs, we call this a double covalent bond. Now we get 2 other carbons over there, electrons for carbon. They need another oxygen to come in. Same thing happens. So this is carbon dioxide, and we've got 2 pairs of double covalent bonds, and that's drawn as 2 lines. Okay, there's carbon dioxide. That's how we do covalent bond diagrams. Okay, you have an overlap here. Now be careful. Okay, be really careful, because I've seen the mistake happen a lot in exams. I want to just share with you that mistake. So let me just switch back to my software, and then we're going to switch back to the visualizer, and I want to show you a very common mistake in exams. Okay, a very common mistake, which is drawing too many electrons. Okay, so let's take the ammonia. Let's take NH3. Okay, now we get 1 nitrogen for 3 hydrogen. So we have nitrogen in there. There's my N, and we have to have 3 hydrogens. So we're going to have overlap areas over here, 1 down here, and 1 over there. And these are my H's. Oh, whenever you have a hydrogen, it's always a single bond. Okay, you never have double hydrogen bonds. It's always a single bond, because it has 1 electron and it needs 1 to be shared with. It's always single pairs. So now nitrogen, let me just over here on this. So nitrogen is group 5, so it has a proton number 7, which means it has 7 electrons. It's got 2 in the first shell and then 5. So we've got 1, 2, 3, 4. I'll just draw 1 down here, 5. So there's my 5 nitrogen electrons. Now 3 of those are going to be shared as single covalent bonds. So we've got 1, 2, 3. Now because these are pairs, I've got to do my dot for hydrogen. So there's a dot, and there's a dot there. So I'm happy I've got my 3 single covalent bonds. But I've seen this done, a mistake so many times. I've used up 3 electrons from nitrogen already. I've got 5 to draw in, so I've only got 2 more to place, and they go there and there. Now I've seen the mistake, and this is a mistake going to be in red. Okay, I've seen people draw this. Okay, they've gone a bit trigger happy with the crosses. They've got the 3 pairs, but they've drawn 1, 2, 3, 4, 5. They've drawn a ton in there. All right, so they've kind of gone over the top with the crosses. It's not the case. You've got to make sure you count the number of electrons you're sharing with the other atoms, and then any remaining, add them in the rest of the circle. So don't go trigger happy with your electrons. That would decrease your marks. Okay, but there's ammonia. Let's have a little chat about ionic bonds. Okay, so let's switch to another bit of paper. Now, I'm going to present to you, I'm going to go to my book for a minute, because there's a few things that we have to consider when we look at diagrams. Okay, so we're going to go to here. Now, this is quite important. There are various diagrams that you can draw. Okay, there's dot and cross diagrams, and then there's what's called 2D space filling, 3D space filling structure and then ball and stick. I would recommend having a little glance over this, everyone, and just have a look at advantages and disadvantages. For example, the 2D space filling says very easy to draw, but it can give the impression the structure is limited to a few ions. It only shows 2D. The dot and cross diagram shows the electronic structure, which it does, but it can give the impression that the structure is made of pairs of ions rather than being a continuous structure containing a massive number of ions. So be careful. These diagrams are good to indicate what's happening between two individual ions, but beyond that there can be limitations, especially for these sort of 3D ones. This one here can show the lattice structure, giving the idea that it's 3D, which is great, but the disadvantage is that it makes you think that there's covalent bonds because there's lines between them. They're not covalent bonds, they're electrostatic bonds. So let's have a little chat about ionic bonds first of all. Now, firstly, what the heck's an ion? Okay, so an ion is an atom that has gained or lost an electron. We have changed the number of electrons. Metals make positive ions. Non-metals make negative ions because metals lose electrons. Non-metals gain electrons. Okay, so let me just get this squared up and let's have a chat. Let's go with sodium chloride. It seems to be the classic one, table salt. So if we look at sodium, and we tend to draw the electrons in the outermost shell only, so we're going to have a dot. Okay, and then we have chlorine, and chlorine is group 7, so it has 1, 2, 3, 4, 5, 6, 7. And so what's going to happen is this electron from sodium is going to transfer from here to here. This electron goes from there to there, and we represent that as squares. So square brackets, we get sodium, and because it's lost that outer electron, we don't draw anything else more. We get rid of it. Now, I'll show you the numbers where they come from in a second. Because chlorine has gained an electron, we draw that as over here a square bracket, and the chlorine, and we have 1, 2, 3, 4, 5, 6, 7 crosses, and then the dot. Okay. Now let's have a little chat about protons and electrons. Over here, sodium as an atom had 11 protons and 11 electrons. So it had plus 11, negative 11 charge, which equaled 0. Chlorine had plus 17 protons. It had negative, or had 17, so it was negative 17 electric charges. This was 0. So these are electrically neutral. But because I've now swapped one, we've lost electrons. This is still 11 protons, but now I've lost the electron. This is now only 10 electrons. Hang on, there's a mistake there. Which means I've got plus 1. I've got 11 pluses, 10 negatives, plus 1. Chlorine, I've got 17 protons. I've now got 18 electrons. I've gained an electron, so I've got a total 18 negative charge. That's going to be negative 1. Negative 1. So that's where these pluses and minuses come from. They come from, if you add up all the protons and all the electrons, because I've changed the number of electrons, I've now got pluses and minuses. Okay. Now, you have to know about ionic bonds. These are attracted electrostatically. Very strong bonds. We'll have a look in a second about the properties of bonds. But I wanted to show you a little cheat method, because we can actually draw this as our formula, which is going to be NaCl. And because there's one of these for one of these, we just keep it as that. But I want to show you a little cheat. It might help you out tomorrow. Let's do aluminium oxides. Okay, this is a bit of a tricky one. So again, that's quite a nice little layout just to refer to this idea of counting the pluses and minuses in your head and knowing which charge to go to. Okay, so let's do aluminium oxide, which is a little bit trickier. So let's get another bit of paper. Let's try that one then. So we've got aluminium, which is, so I'm losing track of my pens. So aluminium is going to be group 3. So it's going to have, we'll do dots. We'll do 1, 2, and 3. Oxygen is group 6, so it has 6 electrons. 1, 2, 3, 4, 5 and 6. And then we have to figure out how many of these do we need for how many of these. And so if we say, well, this one's going to go into there, and this one's going to go into there. Where's this one go? Okay, so remember, I can only react aluminium and oxygen, so I need another oxygen because this has to go somewhere. So let's have another oxygen. So it's going to be 1, 2, 3, 4, 5, 6. So this electron can go into this position. Oh, but I've got another space there now. That's annoying. So I need another aluminium. Okay, so let's do another aluminium. 1, 2, 3 electrons. Okay, so I'm going to use this electron here to fill this gap. Oh, come on, I've got 2 more aluminium. Oh, okay, I've got 2 more electrons to fill up. I know what I can do. I can bring in a third oxygen. So there's some oxygen there. 1, 2, 3, 4, 5 and 6. And now, finally, I've used up all of my electrons and they've filled all my available gaps. Now, in other words, I've had to do that with 2 aluminiums and 3 oxygens. Okay, so the way we, again, I'm just going to do this up here. We've got square bracket, we've got aluminium, which has lost 3 electrons, so it's going to become 3 plus. Oxygen has 1, 2, 3, 4, 5, 6, and then 2 dots. Now it's gained 2 electrons, it's going to be 2 negative. But what about the numbers? Now here's a cool little thing. There's a little cheat, which means the numbers that tell us the charge, if you swap these around, they'll tell us the number that we need. Okay, so this 2 becomes down there. This 3 goes down there. So my formula for aluminium oxide is Al2O3. Okay, you can normally skip this step here, but I'm just doing it for illustrative purposes to show that I need 2 aluminiums for every 3 oxygens, or vice versa. So the numbers up here, the metal plus charge is the number of non-metal ions. The non-metal negative charge becomes the number of metal ions. So there's a little cross there. So there's a little bit on ionic bonds. You have to know about the bond properties. For example, some ionic, so they form crystals, lattice structures, and some of them can dissolve in water. We call that aqueous solution. Some of them can conduct electricity when they are either molten, which means they're melted, or they are dissolved in water. They form strong bonds. And I want to just show you something really quickly, which I'll put in the chat. But I sent it to the Mayfield students on class charts. I will try and find it at the end of this, and I'll put it onto the description for this video. So go back on and look at it, and you find it in the description. I want to show you, I want to share with you my browser again. So it's going to be there. And I want to shut that down and go to this one, the bonding summary. So this, I've got this file on my web space, my greerscience.net. So I want to just spend a little bit of time talking over it. There we go, it should come up. Ignore the police siren outside in my local neighbourhood. So it's going to be loading on any second now. It's just going through. There we go, so it's coming on. Now I can't claim credit for this one. I can't remember where I got it from, but it's quite good. And so it's a little summary sheet for bonds. So I'm going to put it in the chat description at the end of this, and then we shall, and you can download it and look at it, but it's really good summary for C2. Okay, so we have type of bonds. Those are 3 types of bonds. We've then got ionic bonds form giant ionic structures, and that's the network lattice of positive and negative ions. And covalent bonds either form simple covalent bonds like methane, water, ammonia, or they can form giant covalent bonds like diamonds or silicon dioxide, which is sand. and metallic bonds form giant metallic structures, metals. You draw these as the transfer of electrons, usually dots and crosses, and then we're going to have the square brackets with the plus charge and negative charge. It's electrostatic attraction between them, so it's a very strong bond. It forms a giant lattice structure which continues in 3D in all directions. And there's free ions when they dissolve or molten, so it conducts electricity, and it's a giant ionic lattice. And there's some properties there. So forms crystals, high melting point, dissolves in water, some of them do, conduct electricity when dissolved, and conduct electricity when molten. You have to know those things. We'll discuss those later on today when we look at electrolysis. We've got a lot still to cover. There's some examples. Covalent bonds are sharing of electrons. We've done examples of those. There's a single pair, double pair, and so on and so on. We've got dot and cross diagrams. There's single, double, triple bonds. Small molecules. And there's what's called intermolecular forces between those molecules, and they tend to be gases and liquids, so that those forces of intermolecular attraction are weak. So that's why things like methane has a very low boiling point. It's a gas at room temperature. Properties, you have to know those. Examples, you have to know some of those. The giant, this always comes up at some form or another. Giant covalent structures are things like diamond, graphite. The strong and hard high melting points, they do not dissolve in water, they do not conduct electricity. Exceptions are, of course, graphite, and we'll discuss those in a second. Metallic, you've got a sea of electrons, so the electrons are free to move and they're attracted to the nuclei or the ions of the metals, and they form giant metallic structures as well. In pure form, metals are soft and malleable. The layers of ions or metallic atoms can slide across each other or bend. If you introduce another type of metal, it's called an alloy. So that can make it stronger. Again, that's up for your revision to have a look at. And there's some examples. So that's again, I would refer to that one to have a look at yourself, okay? Because it's a lot to cover in this one. We need to do a little bit more work this evening on some more mathematical stuff, and I see the time, it's not too bad. I want to go a little bit quicker, and we're going to keep the knowledge to minimum, more the application now. So again, I'll leave this sort of PowerPoint slide in the description once I've finished this, and I'll add it in later on. Let's escape from this one. Let's go back to the visualizer. Now we have to consider numbers. So let me just get this out of the way, and as another one goes by, who knows what kind of area I'm living in. That's occasionally we get an ambulance, but my goodness, that's 2 police cars. Yeah, indeed, really advertising my home area quite well there. So let's have a think about moles. Okay, there we go. We'll look at moles now. Now this can be quite tricky, so I need your full attention for this one. And I want to begin discussing words, and words can mean numbers. Okay, so if we look at let's think about the word couple. Okay, the word couple, you immediately think of the number 2. If we think about the word dozen, then we think 12. A baker's dozen would be 13. Now there's an old-fashioned one, the word score means the number 20. So words can mean numbers. A century, if anyone likes cricket, then a century means 100. Okay, so words can mean numbers. Now, let me just switch. So I'm going to give you another word, and the word is mole. And just like these words mean a quantity of something, so does the word mole in chemistry. And what it means is this number here. 6.02 times 10 to the 23, sometimes called Avogadro's constant. Now, what does it mean? Okay, let's have a think about it. If we go back to your periodic table, then we've got now the relative atomic mass is all relative to this. Okay, it's relative to carbon. So for example, hydrogen, which is mass of 1, is 12 times lighter than carbon. Whereas if I just go to my table quickly, let's find one that is 24, which is magnesium. So magnesium, which is 12, 24, this would be double the mass of carbon. Relative to each other, this is twice as big as that. That's 12 times smaller than that. Okay, so these numbers are relative to each other. But something happens. Something happens when we get to this number of atoms. Because 1 mole of carbon is equal to 12 grams. 1 mole of magnesium is equal to 24 grams. So this big huge number of carbon atoms has an exact mass of 12 grams. So the relative atomic mass of an atom, if we take enough of those atoms, in fact this many of those atoms, we'll get this exact number but in grams. Now 1 mole of carbon is 12 grams, 2 moles would be 24 grams. So 2 moles of carbon would be the same mass as 1 mole of magnesium. 10 moles of carbon would be 120 grams, and so on, so on. So a mole just means a whopping big number of atoms, and the coincidence, or the genius, or whatever you want to call it, is the number in the periodic table, the relative mass for these atoms, gives us the number of grams when we have 1 mole of those atoms. Now, we have to be able to do some calculations, and who was asking about that again in the chat? Sorry, but the name is Daniel, I think it was. You don't have to. You won't get a memory, an equation sheet. You'll have to know these equations. So let me give you a couple of them. Okay, or this is the main one anyway, and it is number of moles is equal to the mass divided by mR. Now I've just introduced that into the equation. mR, what does that mean? Okay, so let's have a little chat about mR. mR is called the relative formula. Mass. I tend to use that one for everything, but there is another version which is AR. So it could be OR. Moles is equal to mass in grams divided by AR, and that's going to be relative atomic mass. In other words, it's the top number of our the entry in the periodic table. Carbon's 12. Okay, so if we look at the MR, so the AR for carbon is 12. The MR for carbon dioxide, because oxygen is 16, we've got 2 of those, which is 32, plus 12 is 44. So MR is when we have a compound, so more than one atom type. AR is called the atomic mass, which is just looking at individual elements. Now for C3, we have to use this equation in a particular way, and I want to show that to you now by way of a question. And I want to give you Mr. Greer method of doing this. Now I'm not a chemistry teacher, I've had to learn this painfully over the years, and I figured out a way to do this. And now from my friends who are chemistry teachers, they know that I'm terrible at some parts of chemistry. I've had to figure out ways for me to understand it, so I want to present to you my method of doing this next task. Now we have to do what's called balancing equations. Now I want to just quickly have a look at balancing equations before we do the numbers part, because balancing equations is easy, and I've got with me my maths cubes. So there I've got methane, and methane is CH4. And so these little math blocks, so the red blocks is my carbon, the yellow blocks are my hydrogen. Now methane combusts with oxygen, which is O2, and I represent that by having that. There's my O2, there's my two oxygen atoms. So yellow is hydrogen, red is carbon. Now they are going to make, now this is the combustion equation, so it's going to make CO2 and H2O. Now the way we draw that, well actually, so what's happening is all these atoms over here, we have to break those bonds and make new bonds over there. So I've got CO2, which is going to be one carbon, two oxygens, and H2O, which is going to be one oxygen and two hydrogens. Hopefully this is a nice visual way to see actually there's a problem. If I count the blocks on the left hand side, if I took these all apart, could I make all of these? And the answer is no, because I'd take all these apart and I'd have too many yellow blocks, too many hydrogen atoms. Equally, I've got two blue blocks here for oxygen, but I need 1, 2, 3 over here. So we have to balance the equation. The way we do that is quite simply count the atoms on the left, count the atoms on the right, and make sure the number of blocks add up. And this is a nice little visual way of doing this, because I know I've got the right number of red blocks. I've got one on each side. Great, my carbons are balanced, but I know that I've got to have at least 3 oxygens. I've only got 2, so I need to have another oxygen in there, which means I've got to make this 2. I've got to have 2 of these, but I've now got 1, 2, 3, 4 oxygens. I've got 1, 2, 3 over here. I know what I can do. I can have another water. So that means I've got to have 2 of these, which means I've got 1 carbon on the left, 1 carbon on the right. Carbons are done. 1, 2, 3, 4 hydrogens on the left, 1, 2, 3, 4 hydrogens on the right. They are done as well. 1, 2, 3, 4 oxygens, 1, 2, 3, 4 oxygens. Perfect. I've got my equation balanced. All of these blocks, if I took them all apart, I could make this on the right hand side, and that's called conservation of mass. Okay, so balancing equations is really called conservation of mass. Now, we don't just deal with blocks, we deal with atoms. So let's see how this works in the real world, in particular the following question. So I'm going to take these blocks away, like so, and let's have a think about this. Now this is a task that we have to be able to do. Okay, now this is distracting for some people, so I'm going to put another bit of paper here. I've done this in portrait. I should have realised that I have to do this in landscape. Never mind. Okay, we're still learning on how to do this one. Now I know the writing is quite small, so I'll talk you through it. Now we've got an equation. Now the key to this is a skill. This is very much going to be in the paper tomorrow, guaranteed. We have to balance the equation, but not using mathematics blocks and counting atoms. We have to use moles and masses. So let me present to you my surefire way of doing this. Guys, I'm conscious of time. I know it's almost 8 o'clock. This might last a little bit longer than planned, but please be patient. These are the main points that come up. We've got this to do, and then we've got to do a little bit on electrolysis and metals, and then a little bit of bond energies, and then we're done. So about 8:30, then I'll leave you to do your own revision, and I'll put that link on there. But this is important, so let's please pay attention to this part. I know there's been good numbers watching this, guys, which is great, but this will come up tomorrow, and it's good that we are able to go over it. I want to just make sure this is a nice way of presenting these questions. So we're told that sodium nitrate, which is this formula here, decomposes, which means breaks up, on heating to give sodium nitrite and oxygen gas, and the formula is given for me. Now we're told what mass of oxygen must be given off in the reaction. We're given the masses of sodium nitrate and sodium nitrite. So we're told that sodium nitrate, which is NaNO3, decomposes to form sodium nitrite, NaNO2, plus oxygen. Now oxygen is O2. Now we're given the mass for this, which is 8.5 grams. We're given the mass for this one, which is 6.9 grams. And we're asked to work out the mass of oxygen. It's simply just a bit of maths. The mass of the reactants have to equal the mass of the products. And so this missing mass here is going to be this number, subtract this number to give the missing one there, which is 1.6 grams. So far so good. But the question might omit part A and just give you part B, which is find the ratio of reactants and products and balance the equation. Okay, now I could balance this using my brain and visualizing math blocks and all that stuff, which is great, but the whole purpose of this question is to show you're working. And so let me present to you my way of doing these questions. Okay, now it's not perfect, but it helps pupils out. So let me show you my method, which is we're going to have 5 rows to figure out. And the first one's going to be the equation. Write down the equation. The second one is write down the masses in grams. The third row is going to be MR, or in oxygen's case, AR. The fourth one's going to be moles. And the last one I always put down as ratio. So we've got equation, mass, MR, moles. Now these three are involved in the equation. That equation I presented to you. This one here, mass, MR, and moles. If I divide the mass by the MR, I get the moles. If I divide the mass by the MR, I get the moles. So that's why I've done it in this sequence. So let's apply this little blueprint to the equation, or the question. So we've got, now even though I've done up there, I'll write it again down here. So we've got sodium nitrate. Now you can apply this to any question tomorrow. Goes to leave a bit of a gap, because we might write a number in there. Sodium nitrite plus O2. There's my equation. Okay, I've done that bit. Let's write down the masses. The mass of sodium nitrate is 8.5 grams. The mass of sodium nitrite is 6.9 grams. And because in part A I worked out the mass to be 1.6 grams of oxygen. Next part is to use the information in the question, which is the individual atomic masses, relative atomic masses, to get the MR for these compounds. The MR for sodium nitrate, now we've got 1 sodium, 1 nitrogen, and 3 oxygens. So it's going to be 23 plus 14 gives me 36. Add 48 for the 3 oxygens, and that gives me 85. No units, it's just 85. Over here, because we're basically the same as this one, but we've lost an oxygen, this becomes 69. Now here's the careful, guys, you need to be really careful with this one tomorrow. O2, oxygen has a mass of 16, but I've got 2 of them. This becomes 32. Now I've not bothered with moles yet, I've not bothered with balancing the equation. This is purely, these compounds have these MRs or ARs. Moles, well, remember, if I divide the mass by the MR, I get the moles. If I divide 8.5 by 85, I get 0.1, that's my number of moles. Same over here, 0.1, but this one becomes 0.05. So there's my number of moles. Okay, and then I have to figure out the ratio. Now there's a bit of a catch here, so let me explain this one clearly. To work out the ratios, I want to try and get whole numbers, because I want to put whole numbers up here if I can. These aren't whole numbers, these are decimals. So I look for my smallest number, which is this one here, and I divide everything by the smallest number. So divide this by 0.05, divide this by 0.05, divide this by 0.05, and what I'm left with is 1, 2, 2. And here's my ratios. So if I've got one oxygen over here, which I do, because that's the mass, and that's the MR. So one of these for every two of these to every two of these. So even though physically I've got 0.1, 0.1, 0.05 moles, the ratios are 2 to 2 to 1. And so we now go back up to our equation and put a 2, and a 1. Now, we don't have to write the 1 in there, but I wanted to show you these numbers match up with the ratio that we've calculated. So you can drop the 1 there, but it's 2 to 2 to 1. And I've done that by doing my little list of calculations. So I strongly recommend you have this in your mind, because it following the blueprint, you can easily work out the following thing. Now, some of the questions get a little bit trickier. For example, they might ask you to work out the end mass. You have to sort of work down this side and then work back up this side. That's up for you to figure out in your revision, but this is the blueprint which works to calculate these things here. Now, there's one other catch, and I want to show you the catch, and it's to do with something called limiting reactants. I'll move this over here. Sometimes we have to figure out which of our reactants is limiting. Let me present to you how we go about solving this one, because this might come up again tomorrow. So we've got to do the same thing as before. We've got to figure out the equation, which we've been given the equation, which is fine. So that's the EQ part. We then got to do the masses. Okay. Now we're told the masses over here. We're not needing to work at these ones, so let's just put down these ones just now. So we've got 4.8 grams for magnesium. We've got 14.6 grams of hydrochloric acid, which is HCl. And let's leave that there. We don't care about the products over here. Let's look at these two. So we've got our mass. The next one in our list, remember, if we look at this little blueprint here, the next one is the MRs. So we've got MRs down here. Magnesium is 24. Hang on, that's not, it's 48. So it's 48. Now, ignore this 2. Okay, do not worry about this 2 just now. Only look at the HCl, because we'll deal with that 2 shortly. So ignore any numbers in front. Look only at the chemicals, the atoms. We get H and Cl. We've got 1 for hydrogen, 35.5 for Cl. So that's going to be 36.5. Now the last thing, before we do the final answer, we've got to put down our moles, and that becomes that divided by that, which is 0.1. That divided by that is 0.4. Now, when it comes to ratios, okay, whenever the question discusses limiting reactants, you'll either be given the balancing of equation, you have to do it using your blocks method, counting atoms. And what this is saying is, I've got 1 magnesium for every 2 hydrochloric acids. And so let's compare our calculated numbers with the numbers from the equation. Something isn't right. So if indeed the ratio was 1 to 2, then if this is 0.1, this would be 0.2. And clearly it's more than that. So that's not right. Other way around, say this was 0.4 moles. This is a 1 to 2 ratio, so this would have to be 0.2 moles. I need 0.2 moles of magnesium to make 0.4 moles of hydrochloric acid, and clearly I don't have enough. So this number here is what's holding me back. In other words, if I use this 0.1, I can only make 0.2, so I've got more than I need. Okay, extra, it's called excess. So this one's called excess. Whereas if this was indeed 0.4, I've got to have had a 1 to 2 ratio. So I've got to have 0.2 here to make this 0.4. I don't have enough of that, so this is called limiting. So by using our little combination on the left hand side, I've been able to figure out the actual number of moles from the masses, and then comparing those moles to the ratios from the balanced equation and figuring out which one's holding me back. The one that's limiting we call limiting. The one that we make more of or have more of than we need is called excess. Okay, that may come up tomorrow, folks. Again, just refer to this little pattern on the left hand side. Right, I'm conscious of time. We've got a few things still to go, so let me just quickly blitz through a little bit of metals. And so let's find the sheet here, and I want to just cover up the sheet to there. Now you have to know this for tomorrow. You have to memorize it. You have to know what it means. Okay, this is called the reactivity series of metals, and the list here is all about metals in the sequence to come in. So we've got a little mnemonic, which is this, which is please stop lazily calling me a careless zebra. Instead, try learning how copper saves gold. Please. Get that last little bit there. I added that bit in. Now, that's hard to remember overnight. I appreciate it. However, it does stand, each letter stands for the first letters of the actual metals. So we've got potassium, sodium, lithium, so on, so on, so on. We've got the bits in red. We get carbon and hydrogen in red because those aren't metals, but they're in here anyway for a particular reason. And these are the symbols. Now your job is to figure out which of these reacts with water or acids or oxygen, and there is a little series of equations which you have to memorize and you have to be able to apply. And I'm going to show you those really quickly over here. So we've got, you have to know the formula for metals. A metal and oxygen makes a metal oxide. A metal and water makes a metal hydroxide and hydrogen. Metals and acids make salt and hydrogen. Now the key to this is the salt name, the metal in the salt comes from the metal. The non-metal part of the salt comes from the acid. So sulfuric acid makes sulfates, hydrochloric makes chloride, and nitric acid makes nitrates. You've got to know those three. You've also got to know these ones as well. So we've got a metal carbonate plus acid makes salt and water and CO2. And then this one here, acids and metal oxides make salt and water. Acids and metal hydroxides make salt and water. This one is your classic neutralization reaction. This is acid and an alkali. Makes a salt and a water. For example, lithium hydroxide plus sulfuric acid. The lithium from the metal hydroxide becomes lithium for the salt. Sulfuric acids make sulfate, so lithium sulfate. Again, you've got to know how to name salts. I'll leave that there because we're going to move on to do two final big things. Okay, and I've got diagrams here which are printed. I want to show you, and then we'll stop. We'll do a few more things and then we are done. So here we go. Here we need to think about state symbols first of all. So we've got an S, we've got L, we've got G, solids, liquids and gas, and then we have this fourth one called AQ. Okay, aqueous. And here we've got an ionic compound which is currently solid. The ions are bonded together electrostatically. They form this big lattice. Obviously I've just done it as a 2D one, but they're alternating like this. If I put this solid ion structure or compound into water, then it becomes aqueous. Now aqueous solution means that our ionic compound is now dissolved in water, and that has to be shown as the pluses and minuses, the positive ions and negative ions surrounded by water molecules. So this is dissolved, whereas these were bonded together, and they're now separated in the water. And this, we say, can conduct electricity. Alright, so that is aqueous solution. But what I can then do is, I can take my aqueous solution and I can put electrodes on them. I've connected it to a battery or a cell, plus and minus, but at the moment these aren't named yet because nothing's happening. I've connected this to a circuit, the switch is open. When I close the switch, this becomes the anode, this becomes the cathode. So when that switch is closed, that becomes an anode, that becomes a cathode, and something happens to my particles in here. This is a good little visual reference for tomorrow. Here's what happens. Not only do my negative ions move towards the anode, so making them anode ions. So anode ions have another name, anions. Here, my positive ions move towards the cathode. They are cathode ions, or cat ions. Okay. Now, as well as the original plus and minus, now going towards, so we have the positive, the metals are cations, the negative non-metals are anions. Look what also happens to the water. The water itself rips apart into an H plus and an OH negative, and they are also, the OH negatives are anions, H pluses are cations. So in an aqueous solution of an ionic compound, when we do electrolysis, the metal ions and the H plus go to the negative, the cathodes. The non-metal negative ion and the OH negatives go to the anode. Now, there is a catch. Okay, you've got to know this for tomorrow. You've got to know what happens here. Now here, these are going to lose electrons, and those electrons go into the circuit, and those electrons move around to here, and these pick up the electrons. So here they lose electrons, they go round here, these cations pick up electrons. But we need to make a decision which is seen. So here at the anode, we're going to see oxygen gas bubbling off, unless we have what's called a halide. Okay, so in other words, if these non-metal ions are fluorine, chlorine, bromine, iodine, unless it's those, we're going to see oxygen gas being given off. Okay, so if this is a sodium chloride solution, the chlorine ions are going to go over here. We're going to see chlorine gas being given off. If it's if it's copper sulfate, then the sulfate ions are going to go over here, but they're not halogens, so we see oxygen gas being given off. Over here, the metal ions are going to go over here, and we're going to see the metal if they are less reactive than, where's my table gone? Where's my big huge table gone? So if the metal ions that go over to the cathodes are less reactive than hydrogen, then we will see those metals at the cathodes. If they're more reactive than hydrogen, then we see hydrogen gas being given off. Okay, in other words, we're going to see hydrogen gas being given off unless it's going to be less reactive. Okay, so less reactive. Now you've got to revise that again, folks. So in other words, there's a decision to make. in aqueous solution electrolysis, at the anode, we see oxygen unless the negative ion is a halogen or a halide. Fluorine, chlorine, bromine, iodine. At the cathode, we're going to see hydrogen gas unless the metal ion is less reactive than hydrogen. So you've got copper, silver, gold, platinum. Otherwise, we see hydrogen gas. That's a required practical. I recommend looking up some clips on that one. Now guys, I can see numbers are dwindling. I appreciate it's almost time to go. One last quick one. If we have about 2 more things to go, and then I'll we can go through your revision. What if the ionic solution is not, it says insoluble. Okay, so it's insoluble. Then to make this into a liquid, we've got to use heat. Okay, so we've got to put a flame under it, get high temperature, and we've got a molten solution of, so this could be solid, whereas this is going to be now liquid. It is a liquid version of the ionic solution, and this requires extremely high temperature, so high energy. Then if we then put an electrode, now this, I've drawn this similarly, so we've got electrodes over here. Again, this is the plus and the minus, they're not closed yet. Then when you throw the switch, this becomes the anode, this becomes a cathode, and we have anions, which are non-metal, and cations, which are the metal ions of the molten solution, going to each electrode. Now, this is tricky. This involves high energy input, high temperature. And so, for example, there's one called aluminium oxide. Now, the diagram's a little bit different. It involves electrodes down here, so you have to revise that one. But aluminium oxide requires high temperature. So this Al2O3, sometimes called bauxite, requires about 2000 degrees to get it up to this level, and so what's added to it is a chemical called cryolite, which reduces the temperature at which this needs to happen. Okay, so if you reduce the energy needed to make this molten by using a chemical, then you save on money, you save on, because you use less energy to get it to happen. So it's all to do with getting energy into the molten solution, because it can't dissolve in water. Okay, I've gone really quickly there, but have these little visual references to refer to tomorrow. Look up the words like bauxite and cryolite. I've seen that come up a few times as an exam question. Now, the last thing I want to do, folks, I appreciate time is pressing, we've got 8 minutes, then I'll hang up and give you the links. The last little thing I want to do is what's called bond energies and reaction profiles. So really quickly, we've got 2 types of reaction. We've got exothermic and we've got endothermic. And this is called the relative energy. So this is the energy of the products compared to the reactants. And just keep it really simple. You go on this for tomorrow. Let's find another colour pen. I'll do this one in red. So the energy of the reactants are here. We've got to have this kick and then there. Okay, so this is exothermic. This is the energy of the reactants compared to the energy of the products. And we have this difference. This is called the enthalpy change, or delta H. In this case, this is negative. This little bump here, this is going from here to the top, this is called activation energy. Activation energy. So if we end up lower than we began, then energy is given out to the environment. That's called exothermic. If we, relatively speaking, if we start here and we have our activation energy and we end up higher energy than we began, then this is still delta H, but this is now plus, and this is still my activation energy. Okay, so the activation energy is from the reactants to the peak, and the change in energy is from the reactants to the products. So this is a positive change for endothermic, which means the energy of the products is higher than the energy of the reactants. So energy has to be put into the system, and that makes the environment cold. Whereas for exothermic, energy is given out, and that makes the surrounding area feel hot. Okay, endo and exothermic. You don't really have to know the next bit, but you might have to. A catalyst, if I just do this quickly, a catalyst, so we have a random exothermic reaction. A catalyst just means that we can achieve the same reactants and products energy difference, but we can do it at a lower energy, so it might be something like this. Okay, so the activation energy using a catalyst is lower than it is not using a catalyst. That's fine, but everyone memorize these shapes. If it goes lower, it's endothermic, so exothermic, and gives the energy out to the environment. It feels hot. If it's higher than the reactants and the energy is going into the system, it feels cold because it has to draw energy in from you or the surrounding area. Right, absolute last thing, guys. I promise it will be the last thing, and then we are done. My goodness, it's a bit of a marathon. We're looking at bond energies. Okay, so really quickly, if we think about these again, how do these make these? Okay, physically, I want to make these things over there. So I've got to pull these apart. So pull these all apart like this. So I've broken all those bonds, and then I'm going to make new bonds over here, like what am I doing? Oh yeah, yellow. And then I have to make these new bonds. So I've got what I had before, broken all the bonds over here, made all these bonds over here, and that's called enthalpy change or energy change, which is delta H. And it's really simple. It's the energy to break, take away the energy to make. Now what does that mean? Well, if we look at these, this reaction, we've got CH4 over here, plus this oxygen. I know what I've done, but just bear with me. Okay, that's over here. Take away what I make over here, which is these, and then we have this. But the catch is, because I've got two of these, okay, remember I had to have this extra oxygen to make it balanced. I've got to have this extra water to make it balanced. So here's what we're going to say is we need to break all these bonds. Okay, all these bonds, all these bonds. So I've got a carbon to hydrogen bond, and I've got 1, 2, 3, 4 of them. So that's times 4. I've got an oxygen to oxygen double bond, and I've got 1, 2 of those. That's what I break. I have to put the energy in. What I make, well, I've got a carbon to oxygen double bond, and I've got 1, 2 of those. And I've got an oxygen to hydrogen single bond, and I've got 1, 2, 3, 4 of those. Now here's the cool thing about chemistry. The energy to break these bonds is the same as the energy to make these bonds, and there's a number of associates, kilojoules per mole, and so I'm going to give you those numbers really quickly, and we'll do this calculation. Okay, because I'm sure this will come up in the higher paper tomorrow. So last thing, folks, I promise this is definitely the last thing, because you've got revision to do, and I've got a golf tournament to watch. Actually, I do, so just bear with me for a minute, guys. I want to just finish this off. This is coming towards the end of C5, and then we will, I'll let you go. You've got your revision to do. Now, these numbers, the number associated with a carbon to hydrogen bond is 4 112. The units are this funny sort of kilojoules per mole. Don't worry about the units, you'll be given those. The numbers you'll be given as well, you have to know how to use them. So 412 is carbon to hydrogen single bond. Oxygen to oxygen double bond is 496. Now that's what we have to break. 2 of those, 4 of those. And so we add all those numbers up, and we have to break a total of 4 of those, 2 of those, and that's 2, 6, 4, 0. We have to make all these bonds, so the number associated with carbon to oxygen double bond is 743, and the oxygen to hydrogen single bond is 463. So I've got 2 of these and 4 of those, and that gives me 3, 3, 3, 8. And when I do this break, subtract this make, remember I put the energy in to break those bonds, I get the energy out when I make those bonds. Break, take away, make gives me negative 6, 9, 8. Now remember, going back to those little graphs, if the number is negative, it means it is exothermic. And by the way, the units will be given in the exam space. So if it's a if break, take away, make makes it negative, it's exothermic. We put energy in, we get more energy out as we make the bonds. There might be some examples for endothermic, but I saw this question a couple of years ago where you were given the final answer, but you had to find one of the missing bond numbers. So you had to kind of do this in reverse. So it's break, take away, make gives you an answer. If it's negative, it's exothermic. If it's positive, it's endothermic. And you have to do this diagram situation here. You have to make sure it's a balanced equation. You have to have the right numbers of reactants and products, and then count the number of bonds that you break. Keep track of the numbers and the totals. Count the number of bonds that you make. Add them all up, and then subtract break, take away, make. I'm sure there's a better version or names in chemistry, but as a physics teacher, break, take away, make does the job. And I think, folks, I've taken a lot more than I anticipated, but it's quite a lot to cover. So please do some more revision tonight. Once I stop this, I will. There we go. Once I stop this, I will put the description, the link in the description. Okay. So good luck tomorrow. Please ask your teachers first thing in the morning. The exam starts about 9 o'clock, so you will have a bit of time to go over some things and ask your teacher in person. I'll be there for Mayfield, and your own teachers will be there for your own revision. So good luck with your revision tonight. Get plenty of sleep. Don't have chemistry nightmares. I know it's tough, but it's doable. Okay, so everything I've gone over tonight, it may come up tomorrow. I've kind of gone over the main points and a few examples of how to apply them. But please do some more revision tonight, and I'll see you on the other side. Good luck tomorrow, folks, and see you on Wednesday night for a bit of physics, which is my safe space, which is great. See you later.